Hey everyone, so we're going to continue our discussion with springs being in simple harmonic motion. We already talked about forces. Now we're going to move on to the other part, which is energy. I'm going to try to breeze through this because it's, for the most part, recap from the energy unit. I should have showed this before, but I don't know if I actually had it in a video. But I was going to remind you guys that the way that we find the force, stored in the spring is pretty much by looking at the force versus distance graph. This is actually pretty much true for anything. If we want to know what the force is caused by some force, especially if that force is going to change over time for some reason, what we do is we look at the force versus distance graph, and then we take the area under the graph. That's basically the key aspect to finding out the equation or the value of the work being done. So if we look at this graph, we end up having a triangle. So the work is equal to the spring force, because again, the spring potential. Now, if I do this because this is a triangle, it's going to be 1/2 base times height. So 1/2 the force times the displacement, change in spring length. Uh, because of the fact that it's actually not super common that we know the spring force right off the bat, usually we know the spring constant and how long it stretches. We're going to want to actually replace the spring force with kx, because fx equals kx. We have kx times another x, so that ends up becoming 1/2 kx squared. So that's pretty much where that equation's getting derived from. For the most part, the main thing that we want to talk about, though, because like I said, we're dealing with energy, that we've done that before. What we want to do is start kind of looking at this as actually moving. We didn't really do that with the forces yet. It's still pretty static. So what we want to do is consider this case where we have a spring on a horizontal table attached to a mass, and the mass is allowed to move left and right. And just for simplicity, we're going to say that the surface that it's sliding on is frictionless. Now, this is a pretty common setup because, for the most part, it makes life easy since there's going to be only one force acting on it, the spring force. Now, there are a few things that we want to be able to identify. We want to know which point or points is the potential energy the greatest, which point is the kinetic energy the greatest, which point is the velocity the greatest, velocity being 0, where is the acceleration the greatest, and where is the acceleration 0. So as an object oscillates between its amplitudes, we can identify each of these points, and we want to make sure that we know a reason. Now, if you want, you can pause right now and you could try seeing if you can identify what locations these would occur at. Would it occur at the amplitude or the equilibrium point, or some point in between? And you can compare to see what you get. But I'll go through it right now. So the potential energy, because the spring's potential energy is based off of how much it is either compressed or elongated, if I want to know the potential energy, where the potential energy is the greatest, I want to look for the point where the compression or elongation is the greatest. And by definition, that occurs at the amplitude. So this is going to be amplitude. Now, and that's my reasoning, is because the equation for spring potential is 1/2 kx squared. So max potential occurs at max x. Now the next point is, where's the kinetic energy the greatest? Well, if I'm going by logic, the kinetic energy should be the point because of the fact that there's no other forces acting on this. There's no friction. There's nothing taking energy away, nothing giving energy away. This is a scenario where the energy is constant, but the mechanical energy is also constant, meaning the potential energy that it ends up losing as the spring releases itself has to go somewhere, and it typically goes in the form of kinetic energy. So the point where the kinetic energy is going to be the greatest is the point where the potential energy loses most, if not all, of its energy. And that only occurs when it's no longer compressed or no longer stretched, meaning this is going to occur at the equilibrium point. So at the equilibrium point, the kinetic energy is going to be the greatest because that's the point where the potential energy is the least. Now, notice how I'm using the logic that I'm using is not assumed knowledge. It's not something that I'm making an assumption of. I know I'm starting off with the equation, which is concrete fact. I'm using the equations and whatever I found before to figure out these answers. So you want to make sure that you're trying to do that as well. The next point, where is the point of velocity the greatest? Well, I already know the point where the kinetic energy is the greatest, and the equation for kinetic energy is 1 half mv squared. So that means that this should also be where the kinetic energy is the greatest at the equilibrium point. Now the next point is wanting to know when the velocity is 0. Okay, well, I could do a fairly similar setup that I did before. Uh, since I'm looking for the point where the velocity is 0, that means I want to look for a point where the kinetic energy is 0. And since we already mentioned that this scenario has mechanical energy being constant, being converted between potential and kinetic, if the kinetic energy is 0, that means all of its energy has to be in the form of potential energy. So another way of saying it is that this is going to be the point where the potential energy is the greatest, which we already determined was the amplitude. Again, uh, I want to make sure that I want to reiterate this once again is that uh, the the answer that I'm getting to isn't nearly as important as how I'm getting to this answer. This is the type of logic that you need to make sure that when you answer free response questions, when you answer things like that on this AP test, that you're trying to do. You're trying to use, start with an established fact, such as potential energy being 1 half kx squared, and make small statements based off of that. Like I said, the equation is there's a direct relationship or an exponential relationship between compression and energy. Therefore, greatest energy happens at greatest compression. Because there's no friction, mechanical energy is conserved. Therefore, potential goes to kinetic equally. Therefore, yada, yada, yada. So again, pay attention to how I'm wording a lot of the statements because this is how you're supposed to answer questions. As you've probably noticed, some of the questions you end up answering on tests and homeworks, uh, you kind of end up having the correct answer, but you find yourself losing points. And you might be wondering, why am I losing points when I kind of said that? And the reason is because you're not saying it properly. Unfortunately, the way the AP is set up, you have to make very specific comments in order to get the credit. Skirting the edge, dancing around the bush, uh, those don't get you the full points. You have to be very precise in your statements. You need to make sure that there are no assumptions being made. You have to make sure that every single step in logic is stated and makes sense and kind of brings you in a linear way to where you're trying to go. All right. So moving on, there's two more. Where's the acceleration greatest or 0? Again, I need to figure out an equation that relates to this. Unfortunately, unlike the velocity, I can't use the energy again because there's no equation for potential or kinetic that relates to acceleration. So now I need to think about what information, what variable, what topic is pretty much directly linked with acceleration. What is the one thing that the moment I see acceleration, my mind should start making connections to right off the bat before I even finish the question? Well, acceleration is related to force because of Newton's second law, F net equals ma. So maybe instead of asking which point is the acceleration the greatest, maybe I should be asking myself which point is the force the greatest. Well, now that shows me exactly what the equation I'm supposed to be looking at. I want to look for the force of a spring. The force being, where is it? F equals kx. There's a direct relationship between force and x, just like there is a direct relationship between acceleration and force. Therefore, if the acceleration is the greatest, the force is the greatest, and if the force is the greatest, the compression is the greatest. The change in the length is the greatest. So where does this occur? This occurs at the amplitude. And at which point is the acceleration zero? It's going to be the point where the force is zero, the point where the compression is zero. So this would be at the equilibrium point. And this kind of makes sense at basically as when it gets as far as possible to the amplitude. That's the point where it's starting to change directions. And then as it's going towards the equilibrium point, the force is still pointed towards the equilibrium point, but once it passes the equilibrium point, the force starts kind of pushing it back because again, the force is restoring it, trying to push it back to equilibrium. So it makes sense that once it passes the equilibrium point, and the force basically flips over, it has already reached its maximum value and will start to decrease. Well, the deceleration will start to increase, causing the velocity to start to decrease, because of the acceleration now pointing in the opposite direction. So it makes sense conceptually. And you want to make sure that you understand what's going on, the mechanics, but also what's going on through the equations. All right. So this is just kind of recapping everything that I mentioned. The idea that what do we know at the amplitude and what do we know at the equilibrium point? This is extremely important to know because a lot of times what you're going to do is you're pretty much guaranteed to have to make some sort of graph, whether it's an energy graph, a velocity graph, or any typical motion graph, a force graph, something. And one of the best ways of setting up the graphs is not by drawing lines that you think make sense, but by plotting certain points at key moments. So, for example, let's say I wanted the potential energy as a function of position, right? Well, there's three main points. There's this point. This is the equilibrium point when it's zero. There's this point, which is the negative amplitude, which is over here somewhere. We have this point, which is the regular amplitude. Well, I know that at the amplitudes, potential energy is its maximum value. So I can plot a point here and here to show that the amplitude is at its maximum value. And because it doesn't really matter which amplitude we're talking about, that value should be the same. At the equilibrium point, x equals 0, I know that potential is 0 as well. So I plot my 0 point here. From here, if this was a free response question, I've already gotten a majority of the points that I could. So if this question was 3 points, I've already gotten 2 of the 3 points by knowing where these important moments are and connecting dots. So let's say I don't really understand what the line should look like, but I know that it has to go from here to this point to this point. So if I drew a line like this, straight line, make a big V, this is technically wrong, but it would get me a good portion of the points. It would save me a lot of credit on the test. And this is the type of skill that you want to master, is being able to identify the key moments in the graph, essentially beginning, origin, or middle, end, something like that. And you want to plot those points, and then you connect a line through them. If you master this ability, then a lot of the graph questions that you see are going to be the easiest points that you get, and they're usually worth a decent amount of points. So you definitely want to make sure you do that. Now, if you actually graphed it properly, instead of being a straight line, it actually would have been curved. So the potential energy in the spring is actually a parabolic curve. This is because of the fact that potential energy is 1/2 kx squared. So there's that exponential relationship showing it should be a parabolic. So again, this would have been the correct graph, having it be curved connecting to the points, but even if you drew straight lines, you still would have gotten credit, and that's important. What's important is for you to find a way to get the most amount of points as possible, even if you're technically wrong. All right. I already kind of showed how these graphs come about, but once you have the potential graph, the other ones kind of fall into place. Kinetic energy is almost always the inverse of whatever graph it's being converted from and to. So a lot of times when you're making graphs, you usually have almost like a one-to-one conversion where the it's going from one form of energy to another, potential to kinetic, kinetic to work, or something like that. And typically the graphs will always be kind of flipped versions of each other. So potential energy is I forgot exactly the proper term is, but we'll say a upward facing parabolic curve. The kinetic energy will be a downward facing parabolic curve. And then total energy, because of energy being conserved, there's no friction, yada yada. The value should be constant. If I take any point, like this point right here, and I add the energies at this point, I should get the total energy. If I add this energy and this energy, I should get the total energy. So any point, single point, I take the potential and the kinetic, I should always get the total energy. And for the most part, this relationship is sort of true for all simple harmonic motions. In particular, like I said, we're mainly focusing on springs and pendulums. There are other types of simple harmonic motions which the graphs wouldn't look exactly like this, but they're close enough. All right, so here's the first question. So pause video work itself. We'll go over in a second. All right, so the first question is, what is the maximum kinetic energy of this mass? Well, this object is going on in simple harmonic motion. We know its maximum kinetic energy occurs at the equilibrium point. Based off of our understanding, we don't have enough information to figure out anything about the kinetic energy using that equation, so I have to use conservation of energy. I know that the kinetic energy is coming from potential, spring potential in particular. So the maximum kinetic energy is going to be equal to the maximum potential energy. So I use 1 half kx squared, though I'm going to plug in A for x because A is the maximum compression, the maximum elongation. So I end up having the maximum kinetic energy as being 1 half ka squared. Now part B says, what is the massive speed as it passes through equilibrium position? Now, this is actually why I want to focus so much on figuring out and remembering what occurs at the equilibrium point, what occurs at the amplitude, what values are maximum, what values are zero or minimums. And the reason is because of this. If you didn't remember that, you would have seen A and B as two different questions. The maximum kinetic energy and the speed at the equilibrium point. There's no explicit statement that those have to be related. But because of our understanding of simple harmonic motion, we know that the maximum kinetic energy occurs at the equilibrium point. Therefore, this is basically saying what is the mass's maximum speed. So maximum speed will be related to maximum kinetic energy. So I set 1 half ka squared equal to 1 half mv squared. Solve it, and end up getting this. A rad k over m. If you wanted to, you could have left the a underneath the radical. There actually is a reason why I write it like this, but you don't need to worry about it. All right, and then part C asks, what's the total mechanical energy of the system? Now, this actually is trickier than what a lot of people might think. The thing that you have to remember, first off, that mechanical energy is potential plus kinetic. So right there, that's something that a lot of people forget. But you have to remember that when it comes to finding the total energy, you have to pick a single point. In particular, the two notable points are the equilibrium point or the amplitude. So one mistake that people are going to make is that they're going to do Kmax plus Umax. And you can't do that because those two values occur at different locations. So you can't say the total energy of the system based off of energy at one point and energy at another point because they've changed values between those points. So when I do this, what I'm going to do is focus on the amplitude. I'm going to say mechanical energy is the kinetic energy at the amplitude plus the potential energy at the amplitude. Well,
I know that the kinetic energy at the amplitude is zero because the velocity is zero because it's all in the form of potential energy. I already know that what the maximum potential that the potential energy is its maximum, which is 1 FKA squared. So my mechanical energy is 1 FKA squared. If you try to add max potential plus max kinetic, you would have double counted essentially. You would have gotten Ka squared and been off by a factor of two. So you want to be careful with that. That when you're doing energy like this, that you're picking one specific point and you're adding the energy at that location. So again, either pick the amplitude or pick the equilibrium point. Here's the next question. Pause video, works up, and we'll go over in a second. All right. So when we go through this, it might seem like this one's going to be a little bit tricky, but we actually kind of already did this. Remember, one of the things that I mentioned before is that the best way to do these problem solving, develop your problem solving skills. First, you want to try to break down the problem, try to identify which topics we're even focusing on, what aspects are important, what information really isn't important. Sometimes it's actually useful to almost like reword the question or rework the scenario to make it a little bit simpler by throwing out certain pieces that aren't really important, like the ideal massless spring isn't really that important. You go through others, but I don't want to do it right this second. And you want to kind of compare this question to previous questions we've done before. The reason I'm pointing this out because technically question 5, this one, is question 4. Part A is in part B. I want to know what the maximum speed is. Well, the maximum speed is the speed of the object at the equilibrium point. The speed at equilibrium point is going to be, or the speed gets us kinetic energy, which is a maximum, and we know that the kinetic energy is a max um, that's equal to the maximum potential energy stored in the spring, which occurs at the amplitude. So I have these two phrases, amplitude and max speed. So I have essentially a way to find max potential and max kinetic. So I'm going to set those equal to each other.
All right. Sorry, I had a little typo on the screen, but once we set the equations equal to each other, we solve for k, and we end up getting k equals md squared over a squared. Easy peasy, lemon squeezy. All right. And that's pretty much it when it comes to energy and how it relates to the simple harmonic motion. So we're starting to already see how we're dealing with these problems with the springs actually in motion. And this is going to help us when we get to the point where we actually start graphing things and we actually do start taking into account with motion. There's one more video before we get to that. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.